Hello and welcome to T1 Day 21 of Honors Precalculus. It's a big day because we get to talk about the unit circle and we get to start with talking about Ferris wheels, which I know you love. So suppose you board a 100-foot diameter Ferris wheel that makes one revolution every 10 minutes. So you have a 100-foot diameter and one revolution every 10 minutes. Sketch an accurate graph of the height, your height as a function of time for 2 complete revolutions. So you're going to be at 0 because you're starting from the ground, and you'll go 100 feet high. So let's make that 20. So if we make that 20, that's going to be 40, 60, 80, and 100. So this is h of t, the height. And then this is time right here. And let's just make it every, make this 5, 10, 15, 20. So you know what? At time equals 5, it's going to be the highest, because at time equals 10, it's going to be back here. So we know it's going to do this, and as we know, midway through at 50, it's going to reach the midline. It's going to reach the midline at 2.5 minutes, and at 7.5, and then the rest would be 12.5 and 17.5. And as we found out yesterday, when you do this, it's going to be these nice curves. They go up and then down and then keeps continuing. It's cyclical. So there it is. And remember, the midline is right here at y equals 50, or in this case we would say h of t, the height. The midline is h of t is 50. So that would be 2 revolutions. I stopped here just because the scale makes it nicer to make that 100. So once you have this graph, it's pretty easy to answer these next questions, which is state all the times that you'll be 0 feet off the ground. You'll be 0 feet off the ground here, 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 like every 10 seconds. And what you can say is it's at time equals 0 plus 10k, where k is any integer. So if you plug in 5 or 6 or 1 or 2, you'll get some multiple of 10, which will place you at the ground. This next question asks, state all the times you'll be at equilibrium. That's the midline. Where will you be at the equilibrium? Well, that's 2.5, 7.5, 12.5, and 17.5. So it's very similar. You start at 2.5, but you're adding every 5k. Every 5k. So every 5k where k is any integer is the answer to this, because it's every 5 seconds, not every 10 seconds. Because you're reaching equilibrium when you're going up and coming down. So we're doing something similar here where it's a 50-meter Ferris wheel, that's what FW means, but you're boarding from a 10-meter platform. So you're never going to be lower than 10 meters, and it's 50 meters, so you're going to go up 20, 30, 40, 50, but you're going 50 from 10, so you're going up to 60. And suppose it takes 5 minutes to make one full revolution, and at time equals 0, you're in the 3 o'clock position, ascending. So 3 o'clock is right here, by the way, right here. So if you're right here at 3 o'clock, it means you're going to be halfway up. So halfway up means you're going to be 25 up from your starting position of 10, so you'll be at 35. So this right here in green is going to be your starting position. Maybe there's a platform really high up. Okay, so it means it's taking 5 minutes to go around. So it means you'll be back at where you started after 5 minutes. So let's put 5 minutes we'll put 5 minutes right here. So it means you'll be back to that point at 5 minutes. So you do one full rotation, but again, you're starting at the 3 o'clock position. So what this ends up looking like is this right here. You end up going up and then down because you're starting at the 3 o'clock position to get up to here. And then you go down again to get to the point right here. But then you're going to go down even further, and then you're going to go back up to get to right there. And that shape right there gets replicated again. So you can write out the same points. You can actually copy and paste. It's kind of fun. You can copy and paste the curves themselves, and you end up with a graph that looks just like this. So you're back at 5, 10 right here. When you break this up, you know it's going to be 2.5, and then half of that is 1.25, 3.75, and you can fill in the rest using the same breakdowns. And then it says, then find all the times you'll be at the top of the wheel. We will be at the top of the wheel here and here. So that's at time equals 1.25, and time is equal to, well, that's going to be plus 1.25, so 6.25. 6.25. And if you wanted to write the general case for this, it would be t is equal to 1.25 plus 5k, where k is any integer. The key for these is really reading comprehension. So where does it start? It starts here, and it's going up. And we know it's going up because it says ascending. So now we get to talk about similar triangles. And you might recall from geometry, two triangles are called similar if the three angles in one triangle are the same as the three angles in the other triangle. Similar triangles are proportional. Okay, so what does this mean? It means in this case, one thing, that angle B here is congruent to angle E, and that's what this symbol means. It means congruent, the same. And then also, angle A is congruent to angle D, and angle C is congruent to angle F. And the way you state that the whole triangle is congruent to the other triangle is you would say triangle A, I like this, I'm going to do this here, triangle ABC is similar to triangle, it's that little tilde squiggle, DEF. So we say they are similar. So now what you get to remember and we get to work with are the basic trig functions, the first three. So there's sine of theta, there's cosine of theta, and there's tangent of theta. And these are just ratios of side lengths. The sine is the opposite side over the hypotenuse. The cosine of an angle is just the adjacent side over the hypotenuse. And tangent is equal to the opposite side over the adjacent. These are just ratios. And you might remember this. SOHCAHTOA. What you see there is the three trig functions. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So those three side lengths are labeled here, and it's just the ratio of the sides. Now, there are three other ratios that you have to remember, and those are called cosecant, secant, and cotangent. These are also just ratios of sides. They are hypotenuse over opposite for cosecant, hypotenuse over adjacent for secant, and adjacent over opposite for cotangent. So it's really, really important that you recognize some of the relationships here. These are the ones that you definitely will remember from SOHCAHTOA. You'll notice that sine right here, see this, opposite over hypotenuse? If you flip it over, you get cosecant. Adjacent over hypotenuse, if you flip it over, you get secant. And if you flip over tangent, you get cotangent. So that's how you remember all six, and you have to remember them. When you see these functions, this is what they mean. They are relationships, they are ratios of side lengths. So the circle we love to use for these trig functions is the unit circle, and the unit circle has a radius of 1. It means that this distance right here is 1. We love that because when the hypotenuse is 1, it makes a lot of the fractions really nice. So we're going to label this point right here xy. What that means is this distance right here is y, and then this distance right here is x. So what this means is when you're working with this triangle, you can find the sine and cosine of this angle right here. So if this right here is theta right here, the sine of this angle, again, so it's opposite over hypotenuse. The opposite side from theta is y, so it's y over the hypotenuse is 1, so the sine of this is just y. The cosine of theta is kato, adjacent over hypotenuse, so that's x over 1 is x. So what that actually tells you is that sine of theta is equal to y, and cosine of theta is equal to x. It actually tells you then that you can also write this as the point cosine of theta, comma, sine of theta, like this. So that's another way to write the point. So there's a lot of terms we're going to work with here, but another relationship you should know is that tangent of theta, another way to write that is sine of theta over cosine of theta. And that works here in two ways, because we can then take these, because we know that sine of theta is y, so that's going to be y over cosine of theta, which is x. So in this case, tangent of theta is y over x. We're going to say The initial ray here, this ray right here that goes like that, that's called the standard position, which is the initial ray, which is a line with a one arrow on it. And then this one right here is going to be called the terminal ray. The angle is swept out going from the initial to the terminal. The initial to the terminal. So let's just start evaluating, because a lot of this is weird in theory, but let's just start evaluating this. So if you're looking at the unit circle and it asks you for these values here, sine of 0 is what's the sine when the angle measure, this angle measure, you can see this triangle right here when theta is 0. So if you bring this ray right here down to the x-axis, the opposite side, what is y going to be? The height of that is actually going to be 0. So when you're looking at this triangle here, it's actually got a height of 0. So the opposite side is 0, and then it's over 1, which is just 0. Pi over 2, that's in radians right there. Pi over 2, and that's going to be equal to, pi over 2 is equal to 90 degrees. So where is that? When this goes all the way up, so if you take this ray and now make it all the way up, because 90 degrees will go to there, what will the height there be of that triangle? The y value will be 1. The y value will be 1. And the hypotenuse, again, is 1, so it's 1 over 1, which is 1. What about sine of 180 degrees? If you went all the way to here, well, what's the height now? What's the height of the triangle? Well, there is no triangle because the height is 0. So again, for sine of 180, it is 0 because the height is 0. What about 3 pi over 2? 3 pi over 2 is when you go all the way to here and you're at this point. What's the y value there? Well, that's 0 comma negative 1. The height is negative 1, so it's going to be negative 1. What about sine of 360? You go all the way back, and the point right here we're at now is 1, 0. So the height again is 0. So 0 and 1s are really important here. Now what about cosine? Cosine is the adjacent, is the x value of each of these points, the x value. So for cosine of 0, you're going to have an x value of 1, because this is the point you're at right here, 1. And then when you go to cosine of 90 degrees, again, 90 degrees is another, that's degrees, so that's pi over 2 radians. It's another way to think of it. What is the x value there? The x value there is 0. And then what is the x value when you're at pi, which is 180 degrees? That's negative 1, because you're right here. That point right there is negative 1, 0. And then 270 degrees, you're right here. What's the x value there? It is 0. And then we do a few more. Cosine of 360, you're back to where you started. So you're back at this point. That point is going to be 1. And then sine of 450 degrees, where is that? 450 degrees, you go around more than once. So you subtract 360 and you end up with 90. So this is actually equal to, right here, sine of 90 degrees. So we actually did that one already. What is the y value of sine of 90 degrees? That's equal to 1. And then this is the x value of cosine of 90 degrees, and that's equal to 0. You'll notice that sine of x, the greatest it can be is 1, and the least it can be is negative 1, and cosine of x is also bounded. So you can never get values outside of 1 to negative 1 when you take sine or cosine, regardless of radians or degrees.